In previous lecture, we have discussed the basic concepts of distributed shared memory, its consistency models, and algorithm for shared memory mutual exclusion. Content of this lecture. In this lecture, we will discuss about distributed minimum spanning tree and also discuss the well-known GHS algorithm from the following reference. Gallagher, Humblett, Spira, a distributed algorithm for minimum weight spanning trees in ACM transactions programming language in 1983. Introduction. The distributed minimum spanning tree MST problem involves the construction of a spanning tree by a distributed algorithm of a minimum weight in a network where the nodes communicate by passing messages. One important application of this problem is to find a tree that can be used for broadcasting. In particular, if the cost of a message to pass through an edge in a graph is significant, an MST can minimize the total cost for a source process to communicate with all other processes in the network. Preliminaries. Weighted graph. This algorithm requires a weighted graph of n number of vertices and m number of edges, where the weights are given to the edges or non-negative weights, and also their weights are the distinct. So, the spanning tree is a tree induced in a graph which is a connected acyclic graph spanning all the vertices of G. So, we have shown you that the red colored edges forms a tree out of the given graph, which we have shown you in the previous slide. Now, that spanning tree which is subject to the sum of its weight is minimized is called minimum spanning tree. So, for minimum spanning tree, the weight of a tree is nothing but sum of all the edges of that particular tree, and it should be the minimum of all possible spanning trees of the minimum weight is called minimum weight spanning tree. Spanning tree formation or a construction algorithms in the classical system is well known in the form of Prim's algorithm and Kruskal's algorithm. But if the system model is the distributed system where the nodes are communicating through the messages and the messages are transmitted with unpredictable delay in a finite predictable time. So, in that particular model, construction of a minimum spanning tree is going to be a challenging task. So, here we are going to see the algorithm of constructing the minimum spanning tree. So, minimum spanning tree means minimum weighted spanning tree in a distributed system we are going to see. Now, we are going to see some of the terminologies which we are going to use in this particular lecture. The first of them is spanning tree fragment. So, any connected subtree of a minimum spanning tree is called the spanning tree fragment. So, here you can see here that the subtree shown as the green edges is called basically fragment, spanning tree fragment. Now, the spanning tree fragment will have different edges which are out of that particular tree and connecting to some other fragments or the nodes. So, an edge adjacent to the fragment with the smallest weight that does not create a cycle is called minimum weight outgoing edge. Take for example that we have seen this as a fragment, and out of this particular fragment we can see that these are the edges which are out of this particular fragment. Among these edges we can see the edge which is given as the red colored edge is of the minimum weight. So hence the definition says that minimum weight outgoing edge. So the edge 9 becomes the minimum weight outgoing edge, and which is popularly known as MWOE in this particular algorithm. Now MST fragment, a connected subtree of the minimum spanning tree. So you can see in this example there are different fragments are possible. So minimum spanning tree properties. The first property, MST property 1, says that given a fragment of an MST, let E be a minimum weight outgoing edge of a fragment, then joining E and its adjacent non-fragment node to a fragment yields another fragment of an minimum spanning tree. Take this particular example that this is a fragment with one minimum weight outgoing edge which is shown as E. So here we can see out of this animation that when then joining E and its adjacent non-fragment node to the fragment yields another fragment of a MST, which is shown over here. Now MST property 2 says that if all the edges of a connected graph have different weights, then the MST is unique. So here in this animation we can see that in this particular tree, let us take an edge E prime, and in this particular spanning tree on that particular graph another spanning tree that is T with another E, and in that edge is E. Now we can see that let E be the minimal weight edge not in both MST. Without loss of generality, E is in T. Now at least with E as a cycle. Now at least cycle edge E prime is not in T. Since weight of E is less than weight of E prime, we conclude that T prime with E and without E prime is a smaller MST than T prime. So basically this particular animation proof shows that if all the edges of the connected graph have different weights, then MST is a unique. So with these two properties, the idea of MST based on these two properties, we can see that we have to start with the fragment of a singleton node as shown over here. Now the next step is to enlarge the fragment in any order by using property 1 and combine fragments with a common node, that is property number 2. So in this process, that means applying iteratively property 1 and 2, we will get the complete coverage and we will get the MST. That means the fragment is continuously growing using property 1 and 2 till it covers as one fragment, and that is a minimum weighted spanning tree. So minimum spanning tree in a message passing model. The message passing model is one of the most commonly used model in the distributed computing. In this model, each process is modeled as the node in a graph. The communication channel between two processes is an edge of the graph. Two commonly used algorithms for classical minimum spanning tree problem are Prim's algorithm and Kruskal's algorithm. However, it is difficult to apply these two algorithms in a distributed message passing model. The main challenges are both Prim's algorithm and Kruskal's algorithm require processing one node or a vertex at a time, making it difficult to make them run in parallel. Both Prim's algorithm and Kruskal's algorithm require processes to know the state of the whole graph. which is very difficult to discover in the message passing model. Due to these difficulties, new techniques were needed for designing the distributed algorithms for minimum spanning tree in this problem setting, that is in the message passing model. GHS algorithm. GHS algorithm of Gallagher, Humblet and Spira 1983 is one of the best known algorithms in distributed computing theory. GHS is a distributed algorithm based on Kruskal's algorithm that constructs the minimum weight spanning tree in a connected undirected graph with distinct edge weights. A processor exists at each node of a graph, knowing initially only the weights of the adjacent edges. The processor obeys the same algorithm and exchange messages with the neighbors until the tree is constructed. This algorithm can construct the minimum spanning tree in asynchronous message passing model. GHS algorithm can run in synchronous as well as in asynchronous mode of communication and computation. In synchronous GHS, it works with non-uniform model with a distinct weight steps. First, initially each node is a fragment, repeat in parallel synchronous phase. Each fragment coordinated by the fragment root node finds its minimum weight outgoing edge, merge the fragment adjacent to minimum weight outgoing edge until there is only one fragment. In asynchronous GHS, it simulates the synchronous version, works with both uniform and distinct weights, uniform models, distinct weights. So, steps in asynchronous GHS, every fragment f has the level which is greater than 0 or equal to 0 at the beginning. Each node is a fragment of level 0. Two types of merges, absorption and join. Overview. The input graph is considered to be the network and links are basically given weights as in the classical problem. Edges represents the communication links. At the beginning of the algorithm, nodes know only the weights of the links which are connected to them. As the output of the algorithm, every node knows which of its links belongs to the minimum spanning tree and which do not. Preconditions. The algorithm should run on a connected undirected graph. The algorithm should have distinct finite weights assigned to each edge. Each node initially knows the weight for each edge incident to that node. Initially each node is in quiescent state and it is either spontaneously awakens or awakened by the receipt of any message from another node. Messages can be transmitted independently in both the directions on an edge and arrive after an unpredictable but finite delay without error. Each edge delivers message in FIFO order. The idea of distributed MST. GHS notations. First fragment is every node start with a single fragment. Each fragment finds its minimum outgoing edge, then it tries to combine with the adjacent fragment. Every fragment has an associated level that has impact on combining fragments. A fragment with a single node is defined to be a level 0. The combination of two fragments depend on the level of fragments. So, if the fragment f wishes to connect to a fragment f prime, this is f and this is f prime, and the level of fragment f is L is less than the level of f prime, then f is absorbed in f prime and the resulting fragment is at the level L prime, that is shown over here. So, the resulting fragment will be f prime and its level will be the same as f prime's level, that is L prime is equal to 2. Now, if the fragments f and f prime have the same minimum outgoing edge and L is equal to L prime, that is their levels are same, then the fragments combine into a new fragment f double prime and the level of this new fragment will be +1 of the earlier fragments which were same as L. So, it will become L plus 1. Now, if the fragments F and F prime with the same level were combined, then combined edge is called the core of the new segment. So, here you can see that the core, this is the core. Why? Because this was instrumental in combining the two fragments F and F prime. So, it becomes the core of the new segment. Then in GHS notation, next thing is about node states. Each node has a state. There are 3 states in which the node will be at a particular instant of time. That is, the sleeping state is initial state. Find statement during the fragment search for a minimal outgoing edge. Found means otherwise when a minimal outgoing edge was found. So, sleeping, find, found, there are 3 different node states. The algorithm. Description of the algorithm. The GHS algorithm assigns a level to each fragment which is a non-decreasing integer with the initial value 0. Each non-zero level fragment has an ID, which is the ID of the core edge in the fragment, which is selected when the fragment is constructed. During the execution of the algorithm, each node can classify each of its incident edges into 3 categories. That is, the branch edges is the first category, are those that have already been determined to be a part of MST. The second type of edge is rejected edge, are those edges that have been already determined not to be a part of MST. Third is the basic edge, are neither branch edge nor the rejected edge. So, the description of algorithm. For level 0 fragments, each awakened node will do the following. First, choose its minimum weight incident edge and marks that edge as the branch edge. Send a message via the branch edge to notify the node on the other side. Wait for the message from the other end of the edge. The edge chosen by both the nodes it connects becomes the core with level 1. For non-zero level fragment, an execution of the algorithm can be separated into 3 stages in each level. First is broadcast. The 2 nodes adjacent to the core broadcast messages to the rest of the nodes in the fragment. The messages are sent via the branch edge, not via the core. Each broadcast message contains the ID and the level of the fragment. At the end of this stage, each node has received the new fragment ID and the level. Converge cast. At this stage, all nodes in the fragment cooperate to find the minimum weight outgoing edge of the fragment. Outgoing edges are the edges connecting to other fragment. The messages sent in this stage are in the opposite direction of the broadcast stage. Initialized by all the leaves, the nodes that have only one branch edge, a message is sent through the branch edge. The message contains the minimum weight of the incident outgoing edge it found. For each non-leaf node, let the number of its branch edges be n. After receiving n-1 converge cast messages, it will pick the minimum weight from the messages and compare it to the weight of its incident outgoing edges. The smallest weight will be sent towards the branch it received the broadcast from. Change core. After the completion of the initial stage, the 2 nodes connected by the core can inform each other of the best edge they received. Then they can identify the minimum outgoing edge from entire fragment. A message will be sent from the core to the minimum outgoing edge via path of the branch edges. Finally, a message will be sent out via chosen outgoing edge to request to combine the 2 fragments that the edge connects. So, that was a brief overview of the algorithm. Now, let us see the execution, how these steps are basically incorporated in the execution of the algorithm. So, in this particular execution example, the fragment with a minimum outgoing edge discovery is shown. That is a special case of 0 level fragments they are sleeping. When a node awakens from the sleeping state, finds minimum edge connected, marks it as a branch of the MST and sends a connect message over this edge, goes into a found state. So we have seen that the node is making a transition from sleeping to find to a found, 3 states of the process, and also send a message, a connect over minimum weight outgoing edge, which is shown as the red color over here. Now this particular connect message will try to combine the fragments. So take a fragment at level L that was just combined out of the 2 level L minus 1 fragment. The weight of the core is the identity of the fragment. It acts as the root of the fragment tree. So the nodes adjacent to the core send an initiate message to the borders relayed by the intermediate nodes in the fragment, puts the node in the find state. So the basic edges yet to be classified can be inside the fragment or outgoing edges. Rejected will always be inside fragment, and branches is an MST edge. So on receiving the initiate message, a node tries to find the minimum outgoing edge, sends a test message on the basic edge, minimal first. On receiving the test message, in case of the same identity, send a reject message, the edge is rejected. Same identity means it is in the same fragment. Same fragment, the connection will lead to a cycle. In case the test was sent in both directions, the edge is rejected automatically without a reject message. In case of self lower level, delay the response until the identity rises sufficiently. In case such an accept message, the edge is accepted as the candidate. So the nodes send the report messages along the branches of MST. If no outgoing edge was found, the algorithm is complete. After sending, they go in a found state. Every leaf sends the report when resolves its outgoing edge, and its children send theirs. Every node remembers the branch to the minimal outgoing edge of its sub branch denoted the best edge. The core adjacent nodes exchange reports and decide on minimal outgoing edge. When decided, a change core message is sent over the branches to the minimal outgoing edge. The tree branch point to the new core. Finally, a connect message is sent over the minimal edge. So when connecting the same level fragments, both core adjacent nodes send a connect message which causes the level to be increased. As a result, core is changed and a new initiate message are sent. When lower level fragment f prime at a node n prime joins the same fragment at a node n before n sends its report, we can send n prime an initiate message with the find state, so it joins the search. When a lower level fragment f prime at a node n prime joins some fragment f at a node after n sends its report, it means that n already found a lower edge, and therefore we can send n prime an initiate message with the found message, so it doesn't joins the search. Forwarding the initiate message at level L. When forwarding an initiate message to the leaps, it is also forwarded to any pending fragments at level L minus 1, as they might be delayed with the response. So we can see that log n is an upper bound on the fragment levels, and the connect message is sent on the minimal outgoing edges only, and there is no deadlock, we have to assume. Then the communication complexity at every but the 0 or the last levels, each node can accept up to 1 initiate accept messages. It can transmit up to 1 test report change route connect message. Since the number of levels is bounded by log n, number of such messages is at most 5n log n minus 1. At level 0, each node receives at most 1 initiate and transmit at most 1 connect. At the last level, a node can send at most 1 report message. As a result, at most 3n messages. So as a result, the upper bound is 5n log to the base 2n plus 2e. So time under the assumption of initial awakening, it is 5n log to the base 2n. Conclusion: distributed minimum spanning tree algorithms are useful in communication network when one wishes to broadcast information from one node to all other nodes, and there is a cost associated with each channel of the network. In addition to the broadcast application, there are many potential control problems for the network whose communication complexities are reduced by having